You have a machine, you dial in a date, and you go back. Maybe you stop a disaster. Maybe you invest in Bitcoin back in 2009.
Or to just stop yourself from getting that terrible haircut in the 7th grade.
Exactly. The dream of the rewind button. It's a universal fantasy.
It really is.
But here's the problem, right? The moment you get there, things get, well, they get messy. If you stop the disaster, do you erase the reason you went back in the first place?
It's the classic paradox. And usually we relegate that stuff to late-night dorm room debates or, sci-fi movie marathons.
But today we are doing something different.
We are.
We're taking that what if and looking at it through the lens of some really serious, heavy-hitting physics.
Yeah, we have a stack of sources today.
Yeah.
That is, it's kind of mind-blowing. We've got a brand new study from Vanderbilt on entropy, classic papers on wormholes.
Yes, actual wormhole physics.
And a deep dive into how pop culture, from Avengers to Harry Potter, actually gets a lot of this stuff right.
What fascinates me about this stack is the core conflict. You have general relativity, Einstein's big theory, which basically says...
Sure, the math allows for it.
Right. But then you have causality, the rule that cause must come before effect, just screaming, absolutely not.
It's the clash of the titans. Physics versus logic.
So our mission today is to figure out, do we live in a universe where the past is written in stone?
Or do we live in a multiverse where every decision shatters reality into a million pieces?
The paradox trap. Let's dive in.
Let's do it.
Okay, so let's unpack this, starting with the basics, the yes but of time travel physics. Because according to NASA, and specifically Einstein, time travel isn't just possible.
It happens all the time. But there's a big catch.
A huge catch.
Einstein's special relativity gives us a very clear path to time travel, but only in one direction.
Forward.
Forward. It's the fast forward button. It's called time dilation. If you get in a spaceship and travel at, say, 99.5% the speed of light for 5 years, when you come back to Earth, your classmates won't have aged 5 years. They'll be 50 years older.
Which is wild to think about. You've effectively traveled into their future. But, and here's what everyone really wants.
The rewind.
We want the rewind. We want to go back.
And that is where general relativity comes in. Einstein's equations allow for space-time to curve. And if you curve it enough, theoretically, you can create a loop.
Physicists call these closed time-like curves, or CTCs.
Right. It's a circle in time, you walk forward, and eventually you end up exactly where and when you started.
Theoretically.
Theoretically, yes. And we have a few blueprints for how to make one. The most famous is probably the wormhole. We have a paper here from Morris, Thorne, and Yurtsever that breaks this down.
I love the analogy they use. A wormhole essentially folds space-time like a piece of paper.
And you poke a pencil through.
Exactly. Point A and point B are suddenly touching. But that Morris and Thorne paper highlights a massive engineering problem, doesn't it?
Oh, it does. Gravity wants to crush that wormhole shut instantly.
So it's useless.
Well, to keep the throat of the wormhole open so a traveler can actually get through, you need something to push against gravity. You need exotic matter.
Exotic matter. Which sounds like something from a Marvel movie.
It kind of is. In physics terms, it just means matter with negative energy density. It violates something called the weak energy condition.
So it pushes rather than pulls.
Precisely. We don't have jars of this stuff lying around.
Not yet, anyway. But there's another mechanism in our stack, the Tipler cylinder.
Ah, yes.
Yeah.
Frank Tipler. This is a deep cut.
Yeah.
The idea is that if you take a cylinder, just imagine a massive pole, and rotate it along its axis incredibly fast, it drags space-time around with it. It's a phenomenon called frame dragging.
Like spinning a spoon in coffee and watching the foam swirl?
Perfect analogy.
Yeah.
And if the cylinder is massive enough and spins fast enough, it tilts the light cones, which define the path of time, so far over that forward in space becomes backward in time.
Oh, pop culture check. This shows up in the visual novel Steins Gate and even in Star Trek Online.
They use them as literal time machines. But, and here's the yes but. Again, Stephen Hawking had a few things to say about this.
He was the ultimate buzzkill for Tipler cylinders, wasn't he?
He was. He argued that for this to work without collapsing into a black hole, the cylinder would have to be infinite in length.
Infinite, so slightly larger than the budget allows.
Just slightly. Hawking proved that if you try to build a finite one, you're right back to needing that negative energy exotic matter to keep it stable.
So it's either wormholes or spinning cylinders, and either way, the math says maybe, but the engineering says good luck finding the fuel.
That's the problem.
Okay, so let's just Let's assume for a second we find the fuel, we build the machine, we go back. Now we run headfirst into that philosophical brick wall, the grandfather paradox.
The classic. You go back, you kill your grandfather before he meets your grandmother. So you were never born.
So you can't go back to kill him.
So he lives, you are born, you go back. It's an infinite loop of impossibility.
We see this in Back to the Future. Marty messes with his parents' meeting, and he starts vanishing from the photo. The timeline is rejecting him.
Right, Back to the Future assumes the timeline is fragile, that it can be broken. But there's another theory, one I find incredibly compelling.
And what's that?
It's called the Novikov self-consistency principle.
This is the you can't change the past theory.
Exactly. The Russian physicist Igor Novikov argued that the universe essentially forbids paradoxes. If you travel back, you are always part of the past. You don't change history.
You fulfill it.
You fulfill it.
The best example of this has to be Harry Potter and the Prisoner of Azkaban.
Oh, absolutely. Perfect example.
Harry gets saved by a mysterious figure across the lake. Later, he travels back in time and realizes he is the figure. He saves himself.
There was never a version of history where he died. He had to go back because he had already been there. It's a perfect, closed time-like curve.
Cause and effect form a perfect, unbreakable loop. And what's fascinating is that we have actual experiments that sort of support this.
You're talking about Seth Lloyd at MIT. The photon experiment.
The suicidal photon experiment.
Essentially, yes. They tried to send photons back a few billionths of a second to terminate their earlier selves, to create a paradox.
And what happened?
The results were spooky. The closer the photon got to creating a paradox, the more frequently the experiment just failed.
Failed how?
The probability of the paradox actually happening just dropped to zero. It's like the universe conspired to stop it. The gun jams. The car breaks down.
That is wild. It's like the universe has an autocorrect feature. I see you're trying to break causality. Let me just fix that for you.
And that brings us to the new study in our stack from Lorenzo Gavesino at Vanderbilt. He proposes a mechanism for how the universe fixes it.
And it's all about entropy.
It's all about entropy, the measure of disorder. The arrow of time usually says things get messier, you break an egg, it doesn't put itself back together.
Right.
But Gavesino suggests that inside a CTC, the rules might bend. He argues that quantum fluctuations could locally reverse entropy just enough to repair a paradox.
So if I go back and try to stop the Titanic from sinking, maybe a quantum fluctuation causes the steering mechanism to fail anyway, or I distract the lookout.
Something like that. The idea is that the timeline heals itself. It resists change. So in this view, we live in a single, rigid timeline. You can visit, but you're just a tourist.
A tourist in a museum where everything is behind glass, you can't touch the exhibits.
Exactly.
Which is safe, I guess, but kind of depressing. It means free will is an illusion when you go back. But then there is the other option.
The multiverse.
This is the big shift. What if the timeline doesn't repair itself? What if it snaps?
This relies on the many worlds interpretation of quantum mechanics. The idea is simple. Every time a quantum event has multiple possible outcomes, all of them happen. They just happen in different non-interacting branches of reality.
So applying this to time travel, I go back to kill my grandfather. I succeed, but I haven't changed my past.
No. You've just arrived in a new branch. Let's call it World B. In World B, your grandfather dies, and that world's version of you is never born.
But I'm fine.
You're fine. You, the traveler, came from World A. Your history is safe back in your own timeline.
This is explicitly the logic they use in Avengers. Endgame. They even make fun of Back to the Future for it.
They do. The Ancient One explains it to the Hulk. Taking an Infinity Stone doesn't change your future. It creates a new, broken alternate future, a branched reality.
We see this in Dragon Ball Z too. Trunks comes back from a dystopian future to save Goku. He succeeds.
He does. Goku lives.
But when Trunks goes home, his future is still a disaster. He saved a copy of the world, not his own.
And that is the tragedy of the multiverse solution. It solves the paradox. You can kill your grandfather in World B because he's not technically your grandfather. But it raises a really lonely question.
Can you ever really go home?
Exactly. You're just jumping from branch to branch. You're leaving your original timeline behind forever. It turns physics into an existential crisis very, very quickly.
It really does. So we have the loop where you can't change anything, and the branch where you change everything but lose your home. But let's pivot to the hardware again. We have a paper here from Patrick Marquet that proposes a way to actually build a warp drive that functions as a time machine.
This is a fascinating paper. He combines the Gödel universe, which is a solution to Einstein's equations where the whole universe rotates, with the Alcubierre warp drive.
The Alcubierre drive. That's the Star Trek drive, right? Expanding space behind you, contracting it in front.
That's the one. You're surfing a wave of space-time. But if you move faster than light, under relativity, you're effectively moving backwards in time.
But doesn't that still need the unobtainium, the negative energy?
Here's Marquet's twist. He suggests we don't need a chunk of exotic matter. He proposes using circulating electric charges interacting with a magnetic field.
Wait, you mean like electricity?
Highly simplified, yes.
Yeah.
He argues that a specific configuration of electromagnetic field can create an energy density that effectively acts as negative energy. It creates the push needed to sustain the warp bubble.
That feels surprisingly attainable compared to build an infinite cylinder.
It shifts the problem from impossible physics to extreme engineering. And there's another mind-bending detail in his paper about entropy.
Oh.
He argues that for the traveler inside this warp bubble going back in time, the entropy of the universe outside appears negative, the gentropy.
So, the traveler continues to age normally, their clock ticks forward.
Yes.
But if they look out the window, the broken egg is leaping back into its shell.
The universe is rewinding around them.
This reminds me so much of the movie Tenet.
Oh, 100%. In Tenet, they call it inverted entropy. You're moving against the flow of the river of time.
It's a very similar concept, so Marquet is suggesting that mathematically this is what a time machine looks like.
It's a bubble of normal time moving upstream against the current of the universe.
So where does this leave us? We have the theory, we have the blueprints, and we have the philosophical safety nets, loops, or branches.
It comes down to a choice between two very different views of reality.
Lay them out for us.
Option 1. The universe is a strict editor. It demands continuity. If we build a time machine, we'll find we're powerless to change the past.
The Novikov loop.
Right. We're just actors fulfilling a script that was written at the Big Bang.
Then option 2.
The universe is a chaotic creator. Every choice, every time jump, shatters reality into infinite parallel variations. We have total freedom, but no stability.
The multiverse branch. Creating new worlds and abandoning old ones.
And there's a final thought to leave you with. Stephen Hawking's chronology protection conjecture.
He believed the laws of physics would conspire to prevent time travel entirely.
Like the universe destroying the bridge before you can cross it. Maybe vacuum fluctuations would destroy a wormhole the nanosecond you turn it on. But if the multiverse theory is true, maybe the reason we haven't seen time travelers from the future is simply that they're all stuck in world B, C, and D.
They can't get back to us. We're the original world A, waiting for a visitor who can never ever reach us.
It's a haunting thought.
It really is.
Yeah.
Well, on that existential note, next time you watch Back to the Future or Avengers, ask yourself, implies loop or branch, and which one would you actually want to live in?
I think I'll take the loop. I like knowing my grandfather is safe.
I don't know, I kind of like the idea of a new timeline, infinite possibilities. Thank you so much for guiding us through this space-time spaghetti today.
Always a pleasure to travel with you.
And thank you for listening to The Deep Dive. We'll see you, or a version of you, in the next one.